like what's important. What's important? Symmetry, right? Because nature tends to be symmetric. It likes to make things symmetrical, right? Like pretty. If it looks pretty, you're probably on the right track. If you have something that doesn't look very pretty or it looks, a little messed up, regardless of your drawing ability, then you're probably not on the right track. So symmetry was important. What else do we have to consider? Octet rule, right? We had to consider the octet rule, which states what? Yeah, that each atom in the Lewis structure needs to have 8 electrons, except which atom? Hydrogen, right? So each atom needs 8 electrons, except hydrogen, which needs how many? That needs only 2 electrons, right? And so we need 8 electrons around each atom, or they want to have 8 electrons around each atom because they want to look like what? The noble gases, right? And the noble gases are the most stable atoms on the periodic table, which is why they're what we say is inert, meaning they're not reactive, because they're very stable. They don't want to give up electrons, or they don't want to transfer electrons, right? Because they're happy in the state they are. So other atoms kind of want to look like that, and they do that by sharing electrons to then achieve that noble gas configuration, right? So that's why we have the octet rule. Can't even think of anything else that was important for Lewis structures? Knowing the number of bonds, right? So knowing the number of bonds, and I'll put that as kind of like a subpoint to the octet rule, right? Because the number of bonds tells us, how many electrons are stored in bonds, and how many electrons are stored in bonds? 2 per bond, right? So the number of bonds around an atom tells us information, or gives us information about how many electrons are around the atoms, right? So knowing the number of bonds. Which means we also should probably know the number of lone pair electrons. What were lone pair electrons? Yeah, these are electrons that aren't involved in bonding, right? They're just electrons that are still in some energy level around that atom. They're not involved in bonding with other atoms at all. Right? So those atoms are localized, is what we would say, meaning they stay on that nucleus of that atom. All right, can you think of anything else? Maybe some general tips or tricks when you're drawing Lewis structures? Yeah, that was one of the tips and tricks we had, was that hydrogen likes to be terminal or on the outside of the molecule. And what else? There's another set of elements that like to do that as well. Does anyone remember what that was? Not helium, right? Because helium is a noble gas. That's not going to be really involved in bonding. The halogens, right? So there's the noble gases, and right next in group what? What comes right before group 8? Group 7, right? Those are the halogens, right? Halogens also like to be on the outside. Also like to be terminal. And that's not to say that it's always going to be the case, but it's generally how things work. All right, that kind of covers all the tips and tricks that we had, right? Besides that, we had a whole procedure, which I'm not going to write again, for drawing the skeleton structure, putting which element at the center of our Lewis structure? Most metallic, or was another way we could phrase that in another periodic trend. Least electronegative, right? So these are the least. We also have the most metallic or least electronegative element at the center of the molecule. All right, that was another thing that we had to keep in track. So we put that at the center, we draw all the valence electrons, we connect the outer and the inner atom, the outer atoms to the inner atom, and then we check the octet rule, right? If we violate the octet rule, we redistribute electrons either in or out of bonds. If the octet rule is satisfied, then we have a valid Lewis structure for that molecule. Okay, so now that we've recalled some of the important aspects of drawing the Lewis structure. Why don't you guys see if you can figure out the Lewis structure for this compound. And before you draw the Lewis structure, name the compound. And then draw the Lewis structure. All right, so what is the name for this compound? Phosphorus goes first because it's... Why does phosphorus go first? Not because P is first, because it's less electronegative and a more metallic element, right? So the same way when we name ionic compounds, we always put the cation first. In covalent compounds, we always put the more metallic or the least electronegative element first, right? So that's why phosphorus goes first. It's a covalent compound, right? Otherwise, we wouldn't be drawing the Lewis structure. How else do we know it's a covalent compound? Or why do you have to worry about charges for this? Anyone have an idea? They're both nonmetals, right? So they're both non-metal, non-metallic elements, right? Because they're on the right-hand side of the periodic table, upper right-hand side. So they're both nonmetals, which means that this has to be a covalent compound, right? If we have a bond between a metal and a nonmetal, that's how you know it's going to be ionic, right? We can also, if I gave you values for the electronegativity within a certain range between 0 and 1.7, those are going to be covalent compounds. If the electronegativity difference is larger than that, it's ionic, meaning it's going to rip the electron off, right? So this is a covalent compound. And do we include prefixes in covalent compounds? Yes, we do. Do we include the prefix for phosphorus here? No, because we don't put mono on the first element, right? So in the first element of the name, we don't have to put mono there, because a lot of times that's going to be implied. So it's phosphorus, and then we have chlorine is the only other element, right? So how are we going to indicate the name for chlorine in this molecule? Tri, chlor, and then the ending gets replaced by ide, right? So we replace the ending with ide, and we use the prefix tri because there's 3 of them, right? So in covalent compounds, we do worry about the prefix because that tells us how many of that element we have in the molecule. In ionic compounds, what tells us how many of that we have in the molecule? How many elements of that species in the molecule in an ionic compound? Right? Covalent compounds, it's the prefix and the subscript that indicates that. Why don't we have to use prefixes in ionic compounds? Yeah, because they have charges, right? And we need the net charge to be what in an ionic compound? What does the net charge have to be in an ionic compound? 0, right? And so the fact that that has to be 0, that tells us how many of each ion we need. How many cations do we need, and how many anions do we need, so that when we add up the total charge, it's equal to 0, right? So that's key distinction between ionic and covalent compounds. So this is going to be phosphorus trichloride. And then when we're drawing the Lewis structure, any questions about naming this compound or naming in general while we're discussing it? No? Okay. And so when we're drawing this compound now, what element is going to go in the center? Phosphorus, the same reason that phosphorus went first in the name. It's less electronegative and more metallic. So we're going to put phosphorus in the center. And how many valence electrons does phosphorus have? 5, right? And how do you know that? Because it's in group 5 on the periodic table, right? So it has 5 valence electrons around it. And then chlorine is what kind of element? What group is it in? 7, which is the halogens, right? Those like to be on the outside. That's another indicator that we should have that on the outside. It's in group 7, so it has how many valence electrons? 7, right? So I'm going to put 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. All right, so now I've drawn my skeleton structure with the least electronegative, the most metallic element in the center, my more electronegative elements on the outside of this molecule. Right? And so what's the next step after this? We connect the bonds, right? So I'm going to draw an arrow from each valence electrons to form a bond between the outer atoms and the central atom. And each of those are going to come together to now share one electron each that now goes around both of these nuclei. And so when I do that, I get a molecule that looks like this: phosphorus, chlorine, chlorine. Right, so I have a new molecule or a new representation of the molecule. And how am I going to check if this is a valid molecule or not? I have to check to make sure all the elements obey the octet rule, right? None of them are hydrogen, so we don't have to worry about any doublets here. But we do have to check that all of these elements are going to obey the octet rule. And so let's check chlorine first. So how many bonds are attached to each chlorine here? There's one bond to each chlorine, right? There's 3 total bonds that involve chlorine, but we're only checking one chlorine at a time, right? So for example, if we're looking at this chlorine, this has one bond here. So it has one bond, which represents how many electrons? Bond, that's 2 electrons. And then how many lone pair electrons, or how many dots does it have on it? 6 dots, which represents how many electrons? 6 electrons. So we have how many electrons around chlorine? 8 total, right? So does that satisfy the octet rule? Yes, it does. So that's good. So then now, if I checked it for this chlorine looks exactly the same, has the same number of bonds, same number of dots. Same thing with this chlorine right here, so I'm done checking all the chlorines at this point, since we connected all of the outer to the inner atoms already. So let's check phosphorus then. So phosphorus, right, we have how many bonds attached to this phosphorus? 3 bonds, right? And that represents how many electrons? 6 electrons. And how many dots are on the phosphorus? 2. 2 dots. So that represents how many electrons? 2 electrons, which is how many total? 8 electrons. So does that obey the octet rule? It does, right? So that means that this is our valid Lewis structure for the molecule, right? If we've found that something violated the octet rule, what we would do is we would move electrons in or out of bonds to then make sure that all the octets were satisfied. And so in this case, because we were naming it as well, I gave you a binary compound, just means it has 2 elements in there, right? But this molecule, do you think that if I had something like PClFbr, right? So how many elements are in that compound? 4. Do you think that that compound would look any different than this one? In terms of its shape? Obviously we would have different elements, but do you think that the shape or how we drew this Lewis structure would end up differently at all? And if you do think it's different, why or why not do you think it would be different? Or if you don't think it's different, why or why not? Phosphorus is still in the center because it's less in electronegativity than all of the halogens, right? So phosphorus is still going to go in the center in this case, and halogens like to be terminal too. And what can you say about all of those halogens there as well? They all have 7 valence electrons, right? Which means their bonding is going to be very similar to any other halogen. So if we were to guess before going through drawing all the Lewis structures, I would guess that this would probably just look something like that, right? Like it would probably be a molecule that looked very similar to this one that we've just drawn. Why? Because you're still bonded to 3 different halogens. Phosphorus is still the least electronegative. And so that's going to determine that this molecule is probably going to look very similar to that, right? Because valence electrons tell us how we bond and what the connectivity is going to be. Right, so that's just something to keep in mind, recognizing patterns for how many bonds that group likes to form, and then that should tell us or give us an indication of what that molecule is probably going to look like, right? So start to develop a little bit of intuition there. Okay, any questions on Lewis structures or naming? Because we're still talking about it. No? Okay. All right. So like I said, we'll go over some practice. So today in lab, I wrote up on the board just because Canvas is down. I don't know how long it's going to be down, so if you want to take a picture. All you need to bring for the exam is, I can't remember if I said 3x6 or 3x4 or 4x6. I don't remember what the dimensions of the note card were. I think it was like that big, right? With one side of handwritten notes, so you can bring that note card. Only one side, so I'll check that before the exam. And then number 2 pencil. So I know last time we had some people take pens, so I went through and I pulled the Scantron out for all of you guys, but this time I don't want to do that. So make sure you have a number 2 pencil. I'll see if I can bring some extra ones in case you forget. Your calculator, right? So we still have problems that deal with the energy of light. Those involve big and small numbers. You want to make sure you're familiar with your calculator. And then also today in the lab, what we're going to do is we're going to make a periodic table. We're going to draw the periodic trends on there, oxidation states, all of this. So it's going to have very specific information on that. And so you just make sure as long as it's only that information on that, you can use that on the exam, right? So when I check your note card, I just have to see your periodic table to make sure that you don't have a bunch of other things written on there as well. But it'll have a lot of information, right? Like you won't have to memorize the periodic trends, oxidation numbers, and things like that. You can write that directly on your periodic table. I have a feeling if you just get used to using that periodic table, you'll eventually just start to memorize everything anyway. Okay. All right. Any questions on this, what we talked about last time, or what you can bring on the exam? Scantron, I'll have Scantrons for you guys again. Okay. All right, so now we're going to talk about what's not going to be on the exam, right, which is we're going to talk about molecular shapes and intermolecular forces, right? So up to this point, we built up the idea of what is an atom, what's made up of an atom, or what is an atom made up of, and then how do electrons fill the energy levels in an atom, and then how do those atoms then interact with other atoms to form bonds. Now we're going to talk about, well, based off of the bonds they form, what shape does that molecule going to make? And then once we determine the shape that molecule makes, we're going to say, well, how does that molecule now interact with other molecules? And this is pretty much as large scale as we go when we're talking about chemistry, because anything beyond that, you start talking about macroscopic things, right? So this is kind of the largest object we're talking about is large molecules. And so how we determine molecular shape is by something called VSEPR, which stands for valence shell electron repulsion theory, VSEPR, electron pair repulsion theory. And this is just a kind of qualitative way that we look at molecules and how they're connected to each other, how lone pairs or lone electrons exist on these atoms, and how do those interact with each other to give the molecule its three-dimensional shape. And the reason we do that is because the molecular shape is a key feature and if we're determining the functionality of that molecule, right? So for example, if you look at proteins in the body, they are all in a specific three-dimensional conformation, meaning that the way one of the bonds in this protein is oriented is always going to be clockwise, for example. And if you turn it the other way, then that protein goes for something that your body could use and synthesize and use to build up muscles or other proteins in your body, to something that's completely inactive. And it has the exact same atoms in it. It has the exact same connectivity of these atoms, right? So if you draw a Lewis structure, these molecules can have the exact same Lewis structures, but their three-dimensional shape is slightly different. And when they have a three-dimensional shape difference between them, then the properties of that material change, or how they interact with the rest of the body changes quite a bit. Right? So this is a qualitative theory that we're going to use to determine how do Lewis structures then lead to a shape of an atom. Oh, I really didn't realize I had the presenter view. Okay. And so if we have different electron groups on an atom, so that's anything like a bonding pair, a non-bonding pair, or multiple bonds, right? That just means our electrons in bonds. Are they just lone pair electrons that exist on the atoms, or are they existing in multiple bonds between atoms, right? So these are all the things that we define as electron pair groups, right? If we have a bunch of electrons next to each other, what do they tend to do? What do you think they tend to do if you try and put a bunch of electrons next to each other? They repel each other, right? Because they all have what charge? they all have a negative charge, right? So if we look at an atom, so these are all going to repel each other. If we look at an atom, let's say it's something like chlorine, and we know chlorine has, let's say it's bonded to something else. We don't know what it's bonded to, but it's bonded to something else, right? And it has 6 lone pair electrons on it. If initially all the electrons were grouped on one side like this, they're probably going to repel each other to then spread out evenly over the chlorine atom, right? So they repel probably into something where they're equally distant from each other, right? And so each of these lone pairs, in this case, represent an electron group, and the bond itself represents an electron group. And so what this theory says is that, well, since they're all trying to repel each other, we're probably going to create a shape that's going to put them all at equal distances away from each other. So right, we're trying to make the atom as happy as possible. How do we do that? Well, we try and maximize the distance between each of the electron groups without, as a consequence, moving 2 electron groups closer to each other. Right, so this is kind of, if you were to look at, for example, a drum. Has anyone seen where they put salt on a drum or a speaker, and then as the speaker plays, all of the salt eventually moves to specific spots on the surface of the drum or the speaker, right? So they're following the waves. This is kind of like the same thing because these electron groups are charged and they exist as these waves, and so they all move to spots, right, that minimize the energy of the atom, right? Because that's when we're in the happiest state, right? When we move to minimize the energy, and that corresponds to these electron groups being as far apart from each other as they can be. And as these groups move around the atom, that means that they're going to define what the shape is for that atom. And so there are a lot more shapes than what we have here, but these are the shapes that we're going to focus on for this class, right? Any shapes that go beyond this kind of go beyond the Lewis structures that we've talked about, right? So remember I said there's exceptions to Lewis structures. Once you have heavier elements in there, you can have expanded octets, so you don't need just 8 electrons around atoms, you can have more. But these are the shapes that we're going to focus on. And how do we determine the shape? Well, the shape is determined by the electron groups. And so what are the electron groups? The electron groups, we have bonding and non-bonding electron groups. All right, so all this means if we have a bonding group, that's just defined as a bond, right? So when we look at an atom and a molecule, is there a bond that we're looking at? Is there a bond attached to it? Then that's a bonding group that's on the atom. If we have a non-bonding group, that's just defined as a lone pair electron. And so another question you might ask is, well, if I have this Lewis structure and I have, 3, 4, 5, 2 elements here, which element is going to determine the shape of a molecule, right? So we're looking at relatively simple molecules, right? Usually, something that we can easily draw at this point. So if you were to look at something like water or ammonia, right? What element do you think is going to determine the shape of the molecule? Let's say for ammonia, right? Because if we're looking at the number of bonding groups or the number of non-bonding groups, right, we can look at the hydrogens in that molecule. So if I was to draw this molecule right here, what this will look like is NH3, right? That's what that molecule looks like. That's the Lewis structure for this molecule. So do you think the hydrogen is going to determine the shape of this molecule? Or do you think the nitrogen is going to determine the shape? If you guys had to guess, just based off of intuition. Probably the nitrogen, right? And it's because this is the central atom, right? If we're thinking about the shape of the molecule and how the electron groups are, spaced out around the central atom, that's going to give us the overall shape, right? Because if this bond is an electron group, that bond's an electron group, that one is, and this lone pair is, those are what are going to be moving around to then minimize the energy of the whole molecule itself, right? So it's the central atom, which is why here we have the central atom is what determines the shape. So that means that when we draw our Lewis structure, to get the correct shape for the molecule, we need to have the correct atom in the center, right? And we know how to put the right atom in the center because the central atom is going to be which atom? Most metallic or the least electronegative element, right? So the central atom determines the shape, right? So this is, I would say, important to realize because I think the common misconception I see when we're determining the shapes of molecules is that, people get confused. Which atom do I need to look at, right? Because bonding pairs, lone pairs, how do I know which atom to look at? It's always the central atom, which means that if we have something that's not, a simple molecule that has one central atom, then the shape isn't as well defined as it is for a molecule like this. And so based off of the electron groups on the central atom, that tells us the shape of the molecule. So for example, the bonding groups for the shape, the linear shape, right? We have two bonding groups and zero non-bonding groups, right? So that means on the central atom, we should have how many lone pairs? None, right? Because we have zero bonding groups, right? And if we look at the molecule, CO2, right, this is what it looked like. Right? How many lone pairs are on that carbon in the center? How many dots are on there? Zero, right? So that makes sense that that's going to be a linear shape because we have zero lone pairs there. And how many bonding groups do we have? So I put up there that a bonding group is a bond, but another way of phrasing a bonding group is the number of atoms bonded to central atom. Right, so it's not just a bond that's attached to it because the carbon has, 4 bonds that are attached to it, but it only has 2 bonding groups because only 2 atoms are actually bonded to it itself. Because it's a double bond, it'll have a different type of repulsion than just a single bond would. But when we're just getting a qualitative picture of the shape, we don't worry about that. It's just the bond, the number of atoms that are bonded to the central atom that determines that, right? So we have 2 atoms that are bonded to the carbon, right? Because there's 1 oxygen on either side. So that's how we know this is going to be a linear molecule. Why? Because it has 2 bonding groups and 0 lone pair electrons on it. Vanessa?
So when we did H2O,
Mm-hmm.
as an example,
Mm-hmm.
it kind of like the same structure as the CO2, but oxygen obviously had like the non-bonding.
Mm-hmm.
So why is that one considered wet and not linear?
Because if we look at H2O, right, it looks something like this, right? So we can, when we draw the Lewis structure for the first time, I just want to make sure you get the connectivity right, right? So that's why we're not focusing on that on the exam. But because it has these 2 lone pair electrons on there, right? Lone pair, again, non-bonding groups are the lone pair electrons. And it has how many lone pairs on here? 2 lone pairs, right? So it has 2 lone pairs and 2 atoms that are bonded to it, right? Each hydrogen is one of the atoms bonded to it. But what the lone pairs do is because they also have a lot of a negative charge, they push the hydrogens down. And because they push the hydrogens down, we don't have a linear molecule. We have one that's bent now because the hydrogens are pushed down from the lone pairs, right? They're all trying to kind of find the spot on the atom where they're on the central atom where they're most happy. And how do we do that? Well, we keep the electron groups as far away from each other as we can. So that's why it turns into a bent shape. right? And you could say, well, you know, it still has the other lone pairs that are electron groups, but really when we're looking at the shape, we're really only looking at the actual different atoms that are connected to each other. The lone pairs affect the shape, but the shape is determined by how does the atoms look when they're in that orientation, right? In the hydrogen, oxygen, hydrogen is in a bent kind of shape like that. And so that's how we think about these molecules whenever we have lone pairs in there. Is that lone pair is then going to distort the structure that we usually have that's nice and well behaved, right? So here we also have another molecule that would potentially be linear, which is SO2, and we're actually going to, I'll talk about that in a second, because we're going to go through each of these examples here individually for all of the molecular shapes. All right, so we have two bonding pairs for SO2, but there's one lone pair on the central sulfur atom, and that one lone pair is going to then bend the two bonds down. So that's why I end up with another bent shape. Okay, any questions on anything I've written here? Right, so the bonding group, that's a bond. That's how another way we can phrase that is the number of atoms that are bonded to the central atom. And the non-bonding group, those are lone pairs, which are, again, 2 electrons each, right? Each lone pair, because it says pair, that means there's 2 electrons we consider for each lone pair. And so these shapes are going to tell us about the molecular properties, right? The properties of the molecule, because based off of the shape of the molecule now, we can determine if we have a permanent dipole in the molecule or no permanent dipole. So this will tell us if we have a polar molecule or a non-polar molecule. And that's going to be important for then determining what are the intermolecular forces that are responsible for how these molecules then arrange when they're around other molecules. All right, so let's look at the case of linear, right? This is the CO2 molecule, right? So here we have 2 electron pair groups around the central atom, and these were going to be what type of pair groups? Are these bonding or non-bonding for CO2? These were bonding pairs, right? These were bonding pairs, which is the same thing as we have 2 atoms bonded to the central atom. And so these linear molecules, right, we can determine whether it's a polar or a non-polar molecule by analyzing the shape. Now we know it's linear. So these can usually have polar bonds, right? Because unless all the atoms are exactly the same, right, the bond is usually going to be polar, right? There's very few what we'd say, heteroatoms bonded to each other that are non-polar bonds. So these usually have polar bonds, right? Because what's more electronegative, carbon or oxygen? Oxygen, right? So it goes the other way, right? The more electronegative we get as we go to larger group number, right? So carbon is in group 4, oxygen is in group 6, so oxygen is going to be more electronegative. So that means oxygen likes to do what with the electron density around these the central atom? If it's more electronegative, what does it mean to be more electronegative in a covalent bond? Right? Yeah, it likes to pull stronger on those electrons, right? Which means that it's going to imbalance the charge in the molecule, right? The central atom is going to get a little less electron density around it, and oxygen is going to get more, right? And that gives rise to a dipole, right? So we would classify that bond as polar. So that means if we were to draw the dipole, it would look something like this, right? Because this is going to be partially positive, and this is going to be partially negative in that case. Right, so that's one oxygen. What about the other oxygen? What's that doing? It's going to be doing the exact same thing, but what's the only difference? It's going to be pulling in the other direction, right? So the other oxygen is going to be pulling in this direction. So it's going to be partially negative here, and that's going to be doubly partially positive on this central carbon. And so how we think about this is if we have, a tug of war going on between this This is the rope between them, and the position of the rope is the carbon. This oxygen is pulling, this one is pulling, it's the same element, so do you think they pull the same or they pull differently? They should pull the same because it's the same element, right? So they're pulling equally and opposite in both directions. What do you think that means for the, battle tug of war? Yeah, it's not going to really move the electron density strongly in one direction or the other, which means that even though both of these bonds are polar because oxygen pulls the electrons stronger than carbon, because of the shape of the molecule, it's pulling in equal and opposite directions, so it's like it cancels out, right? So we're looking at how are these electrons pulled in every direction, but it cancels out because it's in equal and opposite directions, which means that these molecules are usually going to be non-polar molecules, right? Because we're pulling in equal and opposite directions, there's no total dipole on the moment, right? If we add these arrows together, one points in this direction, they're the same size because it's the same atom pulling, right? So there's no total dipole that exists on this molecule. So these molecules themselves are going to be nonpolar. And so this is an easier molecule to analyze because it's a linear molecule. You can imagine once you start to get more complicated 3D shapes, it might be a little bit harder to see how they become polar or nonpolar. Does anyone have any idea if we had a molecule like this, how we could make this a polar molecule, right? It says usually they're going to be nonpolar, right? Does anyone have any idea how we can maybe alter something here to make it polar? All right, so this one is nonpolar. How might we change this molecule to make it polar? Yeah, if we replace, which atom do you think we would replace here to make it polar? Yeah, let's replace one oxygen with a different atom, right? So let's say, what atom might we replace oxygen with to give us the same shape for the molecule? Yeah, sulfur. Let's replace it with sulfur. Why? So why would we guess sulfur? It's in the same group, right? Which means the same valence electron probably bonds very similarly. And so if we replaced it with sulfur, and you drew the Lewis structure, you would find that this is the Lewis structure that you would get for it, right? And so now we still have sulfur is more electronegative than carbon, oxygen is more electronegative than carbon. And they're still in opposite directions, so we get one dipole that goes in this direction, right? This is partially positive, that's partially negative. But what can you say about the dipole going in this direction versus the dipole going in that direction? Yeah, the oxygen is going to pull more strongly because that's more electronegative than sulfur, right? So if we were looking at the dipole going in the oxygen direction, that's going to be a lot larger, right? We have a much bigger force pulling in that direction. So this would give us partially positive and partially negative as well. But because there's a difference in the strength of the dipole in each direction, it's like we add these two arrows together, we're still going to have some arrow left going in that direction, right? Because it's pulling stronger in that direction. So now, if we added them together, we might have something that is slightly polar in the direction of the oxygen. So then this would end up being a polar molecule, which is why we say most often they're going to have polar bonds, but they're usually nonpolar, right? We say usually because the molecule still has to be symmetric because we have to be pulling equally in both directions. This molecule, it's linear, right, because of the electron groups there, but we're not pulling equally in both directions. One direction is pulling more, right? So that's something to keep track of when we're looking at molecular shape. Okay, any questions on the linear molecule? No? Okay. All right, so what about here? Here we have molecule 3 bonding pairs, right? So these electron pairs are going to be bonding pairs. And we say we have 3 bonding pairs because why do we have 3 bonding pairs? So that molecule on the left is the correct Lewis structure. I know it looks different because it doesn't have a complete octet. The only reason it doesn't have a complete octet is because that's one of the exceptions to the rule. We're not focused on that right now. What's another way we phrased bonding pairs? Do we have any lone pairs on the boron in the middle there? Nope, there's no lone pairs, right? So we know I have 0 non-bonding pairs. Why do we say we have 3 bonding pairs?
That's bonded to the boron,
Yeah.
because the boron is connected to?
So it's not necessarily just because we have, right? So this, I'll tell you, this boron molecule has this shape. And then this molecule, which we looked at last time, which was formaldehyde, also has this shape. These both have the same number of bonding pairs. Why do they have the same number of bonding pairs?
The atoms bonded to the central.
Yeah, we still have 3 atoms bonded to the central atom, right? So both of these have 3 atoms. Remember, the bonding pairs, this is the number of atoms bonded to central atom. Right? That's why both of these have 3 bonding pairs. Even though this one has a double bond to the oxygen, right? This one has a double bond, it's still only attached to one atom right there, which is why that only counts as 1 bonding pair. And so these molecules, when they have 3 bonding pairs and 0 lone pairs, this is what we call a trigonal planar molecule. Right? Trigonal because it's like a triangle. Planar because if you rotate this onto its side, it would be flat. Right? All the electron groups are going to spread out in one plane. Right? That's how they're going to stay as far away as possible from each other. And these are going to have polar bonds the same way a linear molecule will have polar bonds. Because in general, you're going to have elements that don't have the same electronegativity bonded to each other. Sam?
How does this follow the octet rule?
That's what I said. This is the boron molecule is an electron deficient atom. So this is an exception to the octet rule. You're not going to be tested on anything that's an exception in this class. But this one it's called an electron deficient molecule. Boron is okay only having 6 atoms or 6 electrons in its octet. Mm-hmm. But we can use the formaldehyde instead to analyze trigonal planar. And so these are going to have polar bonds most of the time because you're going to have atoms that have different electronegativity bonded to each other. But they're usually going to be nonpolar, especially when we have something like this boron trifluoride. And the reason for that is because if fluorine is going to be the more electronegative element in this case, it's going to be pulling electrons in that direction. And now instead of having 2 people playing tug of war, you have 3 people playing tug of war. But they don't all go, now we're not just looking at a line, right? We're not looking at one dimension. We're looking at how things behave in a plane, right? Because we can pull in the x direction and in the y direction. And so the reason that this works out is because if you add up, if you guys ever take any physics, you'll become very familiar with what vectors are, which have direction and magnitude, right? So if this dipole pulls in this direction, it's pulling this red arrow in the x direction and this blue arrow in the y direction. Those are the components of what make up this arrow right here. And so what can you say about these 2 red arrows? They're equal and they point in opposite directions, right? So when we pull a little bit in each of these directions, those are going to cancel out completely. The blue arrows, what we're saying in a molecule like this, is these blue arrows are going to be smaller than this total black arrow that's going the opposite direction. But these are going to be equal to, the sum of those going down is going to be equal to that going up. So the blue arrows, when we add all of them up, will cancel out with the arrow going up. right? So the same way in a linear molecule, we're pulling equally in the opposite in both directions, so it doesn't change the polarity of the molecule, it stays nonpolar. Here, in a trigonal planar molecule, we just have to realize that it's not just as simple as adding these arrows up, we have to add up the components of the arrows. You guys aren't going to be expected to do this, but this is the justification for why this ends up being nonpolar. These blue arrows add up to the same value as this up arrow, just in the opposite direction. So those all cancel out. So all the directions end up canceling out with each other. So how would we then make this molecule, right, polar? It says usually nonpolar. So how would we make this molecule polar, you think?
To add a different atom.
Yeah, if we changed out one of the fluorines for something that's either less or more electronegative, then all of a sudden the size of the arrow going up, for example, isn't the same as the sum of the two bottom ones, right? So this is how we'll start recognizing the pattern that shapes that are usually nonpolar, the way we make them polar is if we have different atoms at different spots. Why? Because electronegativity is different, which means we're pulling electrons differently. We now have imbalanced the charge in the molecule. Right, so these were the trigonal planar molecules. And so as we add more electron pair groups, some bonding pairs and non-bonding pairs, these shapes, they just get more and more complicated, right? So this is a planar molecule, which is how the arrows for the dipoles are adding up. If we have a molecule, two bonding pairs and one non-bonding pair, right? So two bonding pairs mean we have what on the central atom? Two atoms bonded to it, right? We have two atoms bonded to central atom. Because we have two atoms bonded to the central atom, that means we have two bonding pairs. And one non-bonding pair means we have what on there? If we have one non-bonding, one lone pair, right? So also one lone pair. So this is going to give rise to a bent shape, right? And bent molecules have polar bonds, and these are always going to be polar molecules, even if in this case where we have the same atom on both of these, on both sides of this molecule. And so you may ask yourself, well, why, if they're all the same atom, would we have a polar molecule? Well, if we looked at how these things are pulling in both direction, right? Here we have one dipole pointing down, one dipole pointing down in the opposite direction. And we broke it up into its parts again. What colors did I use last time? The blue and the red arrows. All right, what can you say about the red arrows here, if it's the same atom there?
Are they broken apart for a reason?
Just so that you can see the difference between them. Yeah, I just can't draw them all attached because then it'll make a big jumbled mess like that. And so that's why they're just a little bit separate from each other. But these red arrows should be equal in what direction are they pointing in relative to each other? Opposite. So what do you think? Do you think these cancel out with each other?
Yes.
So these will cancel out with each other. But what about the blue arrows if you add both of those up? Right? They're both pointing in the same direction, right? Now, unlike trigonal planar where we had something else pulling up, we don't have anything pulling up anymore. So we have a net, if you add both those up, both of those are going to add going downwards. Right? So now we have, when we add them up, this is going to give us a net dipole that's going down, right? Because there's nothing to cancel out with what's being pulled down here. And so this is a direct consequence of the fact that the lone pair, which is on the central atom, it's not involved in bonding at all, but it distorts the molecule, right? Because that lone pair wants to be far apart from the bonding groups, the electrons in the bonds. It distorts it, and because it distorts it, now the dipoles aren't pointing in equal and opposite directions. They're now pointing down, which means that this molecule is going to have a net dipole moment. So that means that this molecule is going to end up being polar. And so molecules that are bent, trigonal planar, are always going to end up being polar molecules. So you can think that, okay, if there's lone pairs on the central atom, that's going to distort the shape, and that's going to lead to polar molecules, as a general rule of thumb. Right, so bent molecules are always going to be polar for the purpose of this class. That's because the lone pairs distort the positions of the bonds. And so this is what happens as soon as we introduce a lone pair. If we have a central atom that has 4 bonding pairs and 0 lone pairs, so 4 bonding pairs means what? 4 atoms bonded, right? 4 atoms bonded to central atom, and 0 lone pairs, which means we have 0 lone pairs on the central atom here. And with carbon, if we have hydrogens or halogens there, there'll be 0 lone pairs on that central atom. Right? Now, instead of looking at a molecule that's going to be distributing electrons in a plane like trigonal planar was, it's going to be doing it in 3-dimensional space. And so what this is called is a tetrahedral molecule, right? Tetrahedral, which is this shape right here. It's like a triangular prism, right? We have basically 4 faces that each are composed of a triangle attached to each other. That's what a tetrahedron is. And in the center of the tetrahedron is where the central atom lies. And so the way that this molecule reaches its low energy state, or where it's happy, is by pushing each of these groups as far away as it can from each other, and that's why it forms this shape, right? A polyhedron with 4 vertices, which is where each of the terminal atoms are. And so these, like the other very symmetrical shapes, are going to be polar bonds most of the time because they have different electronegativity, but are usually going to be nonpolar. And so I added up the dipole in the case of trigonal planar, linear molecules, and bent shapes. This one I'm not necessarily going to go. This is going to be too hard to draw how each of the dipoles are pulling in equal and opposite directions, and all the different components end up canceling out with each other. But it's the same principle, right? How do we get rise to a nonpolar molecule? Well, if we broke up all the little dipole arrows into all their components and added them all up, they would cancel out completely. Unless we do what? How would we make this a polar molecule? If we change one of the atoms here, right? So if we go from methane, which is the molecule on the left, to something like chloromethane, and we drew it in a tetrahedron, now the fact that this chlorine pulls harder than all the hydrogen atoms, that's going to introduce a dipole to the molecule, right? So they're usually nonpolar if we have symmetry, but as soon as we break that symmetry by adding a different type of atom around this central hydrogen, it's going to create a polar molecule.
Is the shape gonna change at all?
It does change, like in actuality, it changes a little bit, right? Because this electron density of this bond is going to be different. But if I'm not having you guys memorize the bond angles or anything like that, right? It would be a slightly more distorted tetrahedron, but we're not worried about that. It's still tetrahedral for all intents and purposes. And that'll be similar to, for example, water molecule is also bent compared to the other bent molecule we had was this was the other bent molecule that we had. right? This one is also bent. That bent molecule up there is gonna have a larger bond angle than this one here, because in this water molecule, we have two non-bonding pairs, right? Which means that we have two lone pairs up here, and because there's two lone pairs, that pushes these bonds farther down. So these two become closer to each other. They're both bent shapes, but they're slightly different shapes from each other. Yeah, the angle is slightly different. But like I said, we're not worried. I'm not worried about you guys knowing all the different angles. Just recognizing that that's a bent shape. All right, so two bonding pairs for this one meant what? Two atoms bonded to the central atom. And two non-bonding pairs means what? Two lone pairs, right? Two lone pairs. And how many electrons are in two lone pairs? 4 electrons, right? How do you know that? Well, if I counted up all the dots, right? I have 1, 2, 3, 4. But each one is considered a pair. One lone pair. All right. So this is another bent shape. Two lone pairs, two bonding pairs. And the last shape that we're gonna discuss is trigonal pyramidal. Should be trigonal pyramidal. And so this is gonna have 3 bonding pairs and 1 non-bonding pair, which means we have 3 bonding pairs means what? 3 atoms bonded to the central atom, right? 3 atoms bonded to central atom. And then 1 non-bonding pair means 1 lone pair. And the way we think of this molecule is, well, originally because we have 3 bonding pairs, that looks like something that's trigonal planar, right? Where everything's equally spaced in the plane. But now we have this lone pair that exists up here. And so when we turn it to the side now, that lone pair is going to be pushing all the other atoms down, which makes it look like a small pyramid. Right, so all of these get pushed down. And because they all get pushed down, they all pull electrons down a little bit. There's nothing pulling up to counteract everything that's being pushed down. So these are going to end up being polar molecules. Right, because there's always going to be an imbalance because this one's also 3D, but it's a little easier to see. What did I use for the arrows again? I'll go back in a second. This pulls that way, that pulls that way, that pulls that way. Down, down, down. All the red arrows are kind of pulling in equal and opposite directions. But everything that's pulling down, there's nothing pulling back up to counteract that. So we're always going to have a net dipole moment in these molecules. And when I say net dipole moment, that means you add the arrows together. There's always going to be an arrow left over. They're not going to cancel out. All right, so these are all the shapes that we're worried about, right? So we're not worried about, if you look it up, you'll find that there's other shapes, C-shaped, octahedral, what else is there? T-shape, there's a bunch of other shapes, square, planar, everything that'll give rise because of the heavier elements. But these are elements that are going to be obeying the octet rule, which is why we're focused on these elements here. Okay, and so I'll let you guys go here in a second. I just want to summarize that. Are you still, am I good to go on to the last slide for today? Anyone still writing? Okay. So that these shapes on the right are always going to be polar, and the ones on the left here are going to be mostly nonpolar. And the way we make those mostly nonpolar shapes polar is if we replace one of the atoms with a different electronegativity atom. right? And we just consider symmetry when we're thinking about